This is our follow-up session on log-linear regression. Today I'm going to introduce over-dispersion and count data, instances where the Poisson model does not fit well, and introduce the negative binomial distribution for these applications. I'll introduce zero-inflated count models, and then we'll go through some fitting and interpretation of Poisson and negative binomial with and without zero inflation. I'll start with a quick review of log-linear Poisson generalized linear models, as well as a review of diagnostic plots and interpretation of the coefficients, some things that were only covered in the lab session last time, and then introduce negative dispersion with the negative binomial distribution and zero inflated models. This is all coming from chapter 8 of your textbook. And I also added just some nice tutorials here from this website at UCLA that has code for R, as well as a few other statistical software languages. We're calling these three components of all generalized linear models: the random component that specifies the conditional distribution for the response variable, that is, what distribution that response has conditional on a fixed value of the predictors, that can be normal in the case of linear regression, but can be any number of other families of this exponential family, such as the binomial distribution for logistic regression and the Poisson the Poisson distribution for certain count data. Then the systematic component, this has been the same for all of our linear models. This is this linear function of the predictors. This is the betas, the beta 0, the intercept term, and some linear combination of predictors. And finally, this link function denoted by G that specifies the relationship between the expected value of the random component and this systematic component, the linear predictor. And that link function can be either linear, such as with linear regression, or nonlinear, such as the logit function or the log function that we're using now. So we introduced last time the Poisson distribution for certain kinds of count data, and it is a little bit simpler than the normal distribution and the binomial distribution in that it has only one parameter, and that's this parameter lambda, which is something greater than 0, but it defines both the mean and the variance. This is a formula for the probability distribution of the Poisson distribution, and it's just an ordinary function with a probability, but that only exists for integer values. So here is an example with lambda equals 1, so the mean and variance here are 1, and you see it has its highest values at counts of 0 and 1. Then here is lambda equals 2, where the peak is up around 1 and 2. And then for a larger value, lambda equals 4, we see the peak up here somewhere closer to 4. And the larger this value of lambda is, the more symmetric this distribution starts to be. So using the Poisson distribution in a generalized linear model looks like this. So where this is the expected value of y. Remember that for the Poisson distribution, that expected value of y, that is the mean. The mean is parameterized by this this variable lambda. Our link function is this log, and then on the right side we have a linear predictor, and this is just from the example that we were using in the lab last time, or just taking the exponent of both sides. The parameter of the Poisson distribution is equal to the exponent of the linear predictor. And so that when I said that the conditional distribution of the outcome is Poisson distributed, that means that for one fixed value of all these variables, we have a Poisson distribution with a fixed mean. That mean might be different for every it will be different for every combination of the predictors, but for a given combination, we have a Poisson distribution with a fixed lambda. That is to say that the random part of the distribution is a Poisson distribution with mean lambda. So that the outcome variable y is Poisson distributed with a mean of lambda, where lambda is given by the exponent of the linear predictor. So we're using it as an example, this data set from the textbook, The Risky Drug Use Behavior, where the outcome is the number of times the drug user shared a syringe in the past month. And it has a number of predictors in here, but we're only looking at 3 of them right now: sex, ethnicity, and homelessness. And behind the scenes in this slide, I've filtered so that we have only sex, M and F, ethnicity, white, AA, and Hispanic. And looking at this subset of the data set, just doing the summary, we see this, the minimum number of counts is 0, the first quartile is also 0, the median is 0, that means that half the counts are 0. The third quartile is also 0, that means that actually at least 3/4 of the counts are 0. The mean is 3 and the maximum is 60. So this is clearly not normally distributed. It's also clearly not Poisson distributed. The mean is 3 and the variance is 113. So the variance is much higher than the mean, which is to say that it is over-dispersed. There's more dispersion than we would expect from a Poisson distribution. Making a couple exploratory plots of this data set. This is just a histogram, and we see this huge bump down at 0 and just a few high values. Or plotted another way, this is just the x-axis here is an index, that is, if we rank all of the number of needle sharing incidents for each drug user, from 0 up to the maximum value, and plot the rank against sorry, this is not number of participants. This is number needles shared. We see that only at about, so I don't know, there's about 120 participants in the study, and about 90 of those are 0. And then you see that there are 2 participants here that shared a needle 60 times, and there are a few above 30 times. So you see this very skewed distribution at another look at it here. So when we fit a Poisson log-linear model to this anyways, it looked like this. Linear predictors specified the same way as it always is. And for the family of models, we specified Poisson with a log link. These residuals plots that we only made in the lab session, it's a little bit hard to read this first one, the predicted values against residuals. So these are the predicted number of counts, and what you immediately see here is the maximum number of predicted counts is 2.5, whereas the residuals are up to 30. So none of the predictions are anywhere near high enough for what we actually observe in the data set. And we also see that obviously the positive residuals are much larger than the negative residuals. So when we're predicting 0, I'm not sure why these are showing a little bit negative. That's just something about the scale here. But our minimum predicted value can be 0. We see residuals. Some of those predictions have actual observed counts as high as 10. This normal QQ plot is a little bit, to me, a little bit easier to interpret just in seeing that at this upper end of our theoretical quantiles, so this is where we would expect to see, if it were a Poisson distribution, higher higher counts, the residuals are much higher. So if this were a properly fitted model, we would see all of these points more or less along this dotted line, but it's not even close. So this is not a well-fitting model. And these other two just show more views at this same thing of seeing certain points that are far away from the red line here, and here points that are far outside of these points. For a well-fitting model, most of these would be inside. We wouldn't see such outlier points here. So the Poisson model is definitely not a good fit. This motivates us to start thinking about overdispersion and how to deal with it. So when I say overdispersion, what I'm referring to is that the variance is greater than the mean. That means that the variance is higher than what we expect from a Poisson process. And one such model is the negative binomial distribution. It is not the only one, but it's the only one that I'm going to introduce here. Another option that could potentially help, especially in a case like this where we have many zeros, is zero inflation. So we'll be introducing that later. I'm just going to give a brief explanation of what the negative binomial distribution is, just to demystify it a bit. First, recalling back to the binomial distribution, that was the number of successes in n trials. So for example, if you roll a dice, n equals 10 times, how many times do you see a 6? So the maximum that you could see a 6 would be 10 times, the minimum would be 0 times, and on average you would see it 1/6 of the time, and that was the binomial distribution. So the negative binomial distribution is a little bit flipped. It's the number of successes it takes to observe a certain number of failures. So for example, how many times do you have to roll the dice to see a 6 10 times? So this time clearly there is a minimum. You have to roll the die at least 10 times, but there's no maximum. If you're really unlucky, maybe you have to roll it 1,000,000 times in order to see that 6 10 times. Unlikely, but possible. So that number of rolls is no longer fixed. And just as a note, in the binomial distribution, we referred to the 6 using p with a probability of 1/6. It's reversed in the negative binomial distribution. And here, p in this distribution, p is 5/6, so that a non-6 is the success and a 6 is the failure. Now, there are actually multiple ways to write down a negative binomial model. The way I'm going to talk about, because it's fairly intuitive and it is used by the software that we're going to use, is to parameterize the systematic part the same way as the Poisson model. So this is exactly as we saw it before, but with the random part being this negative binomial distribution with this same centrality or mean parameter lambda, but with a second parameter that we'll call the dispersion parameter that defines how overdispersed the model is, and with a theta equal to 0, that is 0 over dispersion, it is equivalent to the Poisson model. And just as a note, this glm.nb function that we're going to use from the mass package uses this parameterization. The dn binom function that's from the base package uses a different one. But this one is very appealing just because of this simple interpretation of it. Still has a lambda, and if its second parameter is 0, it's a Poisson distribution. If that second parameter is something greater than 0, then it's overdispersed. As a note, we've talked a bit before about nested models. Nested models are ones where they use the same data, but one model has parameters that are entirely contained within the other model. So for example, when we talked about linear models with x1 and x2 as predictors, then another model with only x1 as a predictor is nested within the x1 plus x2 model. Well, in this case, the Poisson model with only lambda is nested within the negative binomial model that has these two parameters, lambda and theta. Now, taking a look at the negative binomial distribution, it is again just a probability distribution. So these are integers on the x-axis here. So these are integers from 0 up to 40 I'm showing here. And these are a couple of, a few different negative binomial distributions. And in this case, I'm using that dn binom function from the base package, so the parameterization is a little bit different. It's not lambda and theta, it's n and p. But the only point that I want to make here is that these parameters affect both where the middle of the distribution is and how dispersed it is. So this one with the circles here, this is n equals 10 and p equals 0.5. And then I'm comparing to that n equals 20 and p equals 0.5. You can see how that's just shifted the mean to the right. And then in this third one here, where I've decreased the probability to 0.3, I've increased the overdispersion of it. So in addition to being able to modify the mean, I'm able to modify the dispersion in this distribution. And comparing it to the Poisson distribution, I fiddled around a little bit to try to get some distributions that have more or less the same middle. So here's a Poisson distribution, two different Poisson distributions overlaid on top of those same negative binomial distributions, just to show that for the same center part of the distribution, the negative binomial distributions have more skew, they have more dispersion. You see counts going up to higher values. So potentially this could fit our needle sharing data set better because we saw that we had too many large values in it. And so the negative binomial distribution does have more high counts as part of its distribution. So fitting it is again easy, except it is possible to fit a negative binomial distribution with the base GLM function, but that does not estimate the overdispersion parameter. For a function that actually estimates both lambda and theta, you need to use this function from the mass package. But if you use that, then the rest of the model is specified exactly the same way. Now the summary of the model looks a lot like summaries that we're used to. It has this call first. I do notice that it says this init.theta. I didn't actually specify this in the call. So let's just ignore this. The rest of this is actually what I specified, and this link is a default value. But we have deviance, residuals, and we have coefficients. And the coefficients, they look like the coefficients just like from the Poisson model, with an estimate, a standard error, a z-value, and a p-value from the Wald test. This you can ignore also. This is something else just coming from it making a use of the GLM call as well. What it's doing is fitting this theta value and then calling the GLM function and saying it's not over dispersed, or it's assuming it's not over dispersed from the negative binomial distribution with this parameter for theta. The rest, so we have the null deviance, that would be the deviance from the intercept only model, residual deviance from the full model, with 4 fewer degrees of freedom because we fit 4 additional coefficients here in addition to the intercept, and a Kaike information criterion value. And then this is something that is different from the Poisson fit that we had. We have also this value for theta. That's that over dispersion parameter, remember? Along with a standard error for it. So this seems to say to us that there is evidence of over dispersion in this data set, in that our theta is more than 0, and even if we go 1.96 times this standard error, it's definitely greater than 0. And it's nicely calculating for us the negative of the deviance as well, twice the log likelihood. So speaking of deviance being negative 2 times the log likelihood, we can use that to do a likelihood ratio test to compare these two models, the Poisson model and the negative binomial model that we just did. And I'm doing it manually here because I've actually found it a little bit not obvious to me how to do it using built-in functions like ANOVA, like we were able to do with 2 GLM models. But it's not difficult. You can take those values from where it said 2 times log likelihood, or you can calculate it here. All you have to do is take the difference. It's twice the difference in log likelihoods, and do a chi-squared test. The difference in degrees of freedom is 1 because we have 2 parameters in the negative binomial distribution and 1 in the Poisson distribution. Don't use the lower tail, and we see this probability, it's something very small. Not surprising, the difference in log likelihoods is, well, close to 600, so it's a huge difference. It's clear that the negative binomial distribution is a better fit than the Poisson distribution. Doesn't mean that it's a good fit, but it's better. Looking at these residuals plots to see is it a good fit still looks pretty problematic. We still see very large positive residuals here in this predicted values versus residuals plot. We still see nothing like the residuals just are like the QQ plot falling along this straight line. And again here, definitely positive residuals larger than the negative residuals, and I don't even know how to interpret this. I wouldn't bother with a strange model like this trying to interpret this residuals versus leverage plot. Usually the purpose of this is to help identify outlier data points, these ones that are numbered. Okay, so numbers 21, 25, and 26 are outliers, but it's hard to say exactly what that means in this model. So we've got one more thing to try today to attain this data set, and that's zero inflation. So what is zero inflation? Unlike the negative binomial distribution, which was essentially the same kind of model, just with a random distribution that allowed for greater dispersion, this is really a different kind of model, and it's what sometimes called a two-step model. And it's called a two-step model because it's a mixture of these two models, and you can think of it as being a stepwise or a hurdle model, where your first step is you have a logistic regression model to determine whether the count for a particular observation is 0 or something else, like Poisson or negative binomial distributed. And then in the second step, for observations that pass this first step, then it is a Poisson or negative binomial distribution for values that are not set to 0 in step 1. So it could still be 0 in this step because there are non-zero probabilities of 0 for these distributions as well. So it's a mixture of these two distributions. What does that look like? So here is, I'm plotting a couple of zero inflated Poisson distributions. First is just a regular Poisson distribution with lambda equal to 2, so that's the one with the circles here. So for the regular Poisson distribution with lambda equals 2, this is the probability of observing a 0. It's about, what is that, 13%? I'll put 0.13. Now we have these two zero-inflated Poisson distributions, and for both of them, the value of lambda is the same. For all of them, it's lambda equals 2. But the second thing here, this sigma value, this is that step 1 probability of a 0. So what that means is that in this model, there's a 20% chance that this count is a 0, independently of its Poisson distribution. And then in that other 80%, it would be Poisson distributed. So that immediately adds 20% to the probability. And then what is the overall probability of a 0? It's going to be 0.2 plus 0.8 times, it was about 0.13. So that equals, I don't know, what we see here, about 0.31. And then in this third case, with the zero inflated probability of 0.4, so for this zero inflated probability of 0.4, there's our zero probability. If I were going to calculate it, I would say the zero probability prob of 0 would be 0.4 plus 0.6 times, and again it was 0.13. So if it makes it past this first step of being a 0, then it still has a 0.13 probability, which works out to around, I don't know, 0.48. So you can see how there are these two components to the model. There's the first one that's like a coin flip, the binomial distribution. This is fit with the logistic model. If that comes out as a success with the probability determined by that step 1 model, then you get a 0. If that turns out as a failure, as a non-zero, then you have the Poisson distribution. Let's actually fit the model. And again, actually fitting the model is not any harder than any of the others, but we do have to make use of another package. I'm using this package called PSCL and this function called zeroinfl. Specify the linear part of the model just the same. The Poisson distribution, it gives a selection of different distributions that you can use, including Poisson and negative binomial and some others, and our data set. Looking at the summary of this object, we see a bunch of familiar things here. This set of count model coefficients looks familiar, except now we have some much more statistically significant results in it for sex and homelessness. But we have a whole second table of coefficients here for this zero inflation model coefficients. So you can see we've actually fit two separate models here on the same data. We've fit a count model and we fit a zero inflation model, and each of them has their own set of coefficients. So this actually is pretty weird, and it's becomes pretty hard to interpret these coefficients now, because you actually can't just interpret these coefficients as we have before. Remember, we interpreted these as like a log ratio of the expected number of counts, meaning that if we exponentiate this, it would tell us the ratio by which men are expected to have a lower number of needle sharing incidents. But it's not exactly that anymore, because sex also has an estimate in the second model, and it's the combination of the two of them that would actually affect the, or would actually predict your difference in needle usage here. So this default model that we've fit here is a fairly complex one and a difficult one to interpret. And I'm actually not a fan of this as a default because of this complexity of the model, and because I think in a lot of cases it would be hard to come up with a justification for why you think all of these would affect a zero inflation in your data generating model as well as your count model. Typically in zero inflated models, you're making some kind of assumption that there actually are two different components to your data generating process. One component that produces exactly zeros, and then for the remainder of them, a count model. It's hard for me to imagine why both of these would have all of the same coefficients. So just a note here that in this default model, the zero inflation model can include any or all of your variables as predictors, and in the default for this function, it is to use all of the variables as predictors. So here's a slightly simplified model. In the second one, I'm going to specify that only HIV status. So in this format here, what's on the right of this bar symbol here is what is used for the zero inflation model. So in this model, I'm going to say that HIV status is the only predictor of in the zero inflation model, whereas I have sex, ethnicity, homelessness, and HIV in the count model, and only HIV in the zero inflation model. So this could be under an assumption of saying perhaps the study participants with HIV are somehow in a different situation. Maybe they have access to new needles that other people in this population don't, and so there's an additional probability if they're taking part in that program that they never reuse a needle, or any number of reasons, but you could imagine justifying using HIV as a predictor for zero needle usage in a way that's outside of the regular count model as predicted by these other things. So in this model, we look down and we see, oh, this is actually a bit of some kind of a coding error in here. I have both HIV positive and HIV yes, so who knows what the difference between those is. That's a data cleaning issue that I won't get into here, but you can just see how at least we do have now. I've added HIV. We didn't have HIV in either model before. We have it now in both in this kind of uninterpretable format here, but we see that it is significant up here in the count model, the HIV yes anyways, and is not significant in the zero inflation model. This significant intercept, by the way, I'll interpret on the next slide, where next I'm going to fit an intercept only model, but this is just to say that we are predicting that there is a separate zero inflation probability that fits this model better than a count model only. So in this final zero inflated negative binomial model, I'm using only an intercept term in the zero inflation term. That is to say that every participant in the study has the same probability of having zero inflation. So in this model, we actually have fewer significant associations in the count model, and also not in the zero inflation model. So maybe this is not as good a fit. And this is the kind of thing that, again, we could compare these models using 2 times the log likelihood in these nested deviance tests or likelihood ratio tests. Just as a note here, for estimating confidence intervals in these models, I recommend you use the confint function without trying to specify which package it comes from. It will automatically, it's defined in several different packages, and it will automatically choose which function is according to the type of model that you're fitting, but it will give you your 95% confidence intervals or any other confidence interval that you ask for using arguments of confint. For these zero inflated models, the residuals plots are not quite as easy to do. They're not built into these packages. So I actually defined a couple of functions behind the scenes here, and I'll put them into the lab codes to make it easy for you to see them. But that actually create the first 2 of the panels. This is that top left panel, the predicted values versus residuals for Poisson negative binomial, zero inflated Poisson, and the zero inflated negative binomial model. And really all of them have these issues with the large positive residuals. All you see that they're not nearly as big for the zero inflated model. We had models for Poisson with residuals as large as 30. The maximum residual is only 5 in the zero inflated negative binomial model. So that is some improvement. There's still some strange behavior here, in that the distribution of the residuals is asymmetric. They're much larger positive than negative residuals, and they're much smaller up around these larger predicted values. You see 2 much larger predicted values occurring for the zero inflated negative binomial model. So that's a positive sign. But looking at the QQ plots, it looks kind of bleak still for all of them. And I'm out of ideas at this point. It's a very unusual distribution, and I think it was a bit of a, I don't know, an odd choice for a textbook example in that it doesn't fit any of these, none of these models fit it especially well. Probably zero inflated negative binomial fits it a little bit better, but it's hard to say. None of them fit it very well. And I would be tempted in a case like this to maybe just give up and binarize the outcome and say people who share a needle at least once versus who never share it, or maybe define more than 5 or something like that and have a couple categories. But it's not an easy distribution to fit. So just wrapping up, these are multiplicative models, again, because they're log-linear models. Fitting these zero-inflated models, it can be problematic. Sometimes you'll have convergence problems, especially with small sample sizes, because you're fitting a lot of coefficients there. And you do have these, what can be quite overcomplicated default models that are difficult to interpret. You can still use QQ plots and residuals plots to assess model fit, and you can use likelihood ratio tests to compare nested models. All right, thank you.